let's get on to the recap for the month of August, and let's do a
What did you talk about in August?
Okay, we talked about transparency, opacity, reflection, refraction, and the faster than light travel of light. Light travels faster than light. All these have to do with the properties of light as it meets objects, specifically objects people are concerned about, like, glass, water, air. They say, well, here we had light go through this material and it's transparent, and then for some reason it doesn't go through the wall, through your cement wall. And you say, why is this one opaque? Why is that one transparent? So we looked at this. And the first thing I want to mention is, one thing is for me to explain the mechanism under the rope model of how transparency works, how opacity works, reflection, and so on. That's one issue. Another issue is why. Why is this material opaque? Why is that material transparent? I haven't gotten to that because right now I have problems getting people to understand what I'm talking about. And I'm trying to compare especially quantum mechanics, mathematical physics in general, against the rope model. And people keep talking about going through, traveling through. They say, well, how does a rope explain traveling through?
Well, that was something that you told me that you opened my eyes to the other day, where I always thought also like the light just goes from my eye to the light bulb, but then you're like, no, there's a big wall of air between you.
People don't believe it.
So it's that air relaying from air molecule to air molecule, the light to my eye and back.
Right.
And I always thought of it in terms of like in space, it would go directly from the light to my eye because there's nothing in between. Mm-hmm. But on Earth, it isn't the same mechanism, I guess you could say. I mean, it is, but there's more steps in between.
Yeah,
it's more like what do you call it, the Newton's cradle, where one hits a whole bunch of balls and then it hits the one
exactly.
on the end. Something like that.
What we fail to realize is that what I have here in front of me, which I take into my nose,
it's not playing no part.
It's a physical object, and the question then becomes: does light go through physical objects? Through objects. Does it go through objects? And people say, well, it goes through air. Well, does it? And so they use this term, go through, travel through. And right now I have a big problem just getting people to understand the theory, what I'm proposing. So I'm just explaining the mechanisms of refraction, reflection.
Before we even get to opacity.
Before we can get to the question, why? Why is this one like that? Why is that one like something else?
What have you explained?
Well, let's look at this. Here we have quantum mechanics. First of all, here's all these properties in one picture. We're going to assume that's a piece of glass, somewhat transparent. So some of the light goes through, you can say, right? If we're going to talk about going through, that's why I put a dotted line there. That's the way quantum sees it. So some of the light goes through, some of it refracts. We don't know why, but it turns a corner, right? Sharp corner. Some of it reflects, comes back, and some of it is absorbed, and whatever is there is opaque. And so these are the possibilities, okay? And that's what I
guess that all happens simultaneously.
Well, to some degree, I think it happens with all materials, and I think quantum will agree with a mathematician. They'll agree with that, right? But here's the quantum reasoning, okay? This is, if you can call it reasoning, this is their line of reasoning, okay? And what we have here is, the first argument is that there are many atoms between you and whatever you're staring at, and that was how stuff works officially says this. And they're pretty important. I mean, they represent the establishment, and they have people who are PhDs working in there, and this is what they're saying: many atoms.
What does that mean?
Well, that means that if you put more air atoms between you and the window, you won't see the window. And the answer is no. Period. At night I can't see the window, but if I turn the light on, a flashlight on, I can see the window. Have I put or subtracted or put more atoms in between my eyes and the window? Obviously not. Something else is going on. So it's not a question of how many atoms I'm going to put between my eye and the window.
That's the wrong counter experiment. Okay. The right counter experiment would be, can you compress air to the point where you can't see through it anymore?
Well,
you have like a tunnel, and again, in that tunnel you compressed air, had so many atoms in one place. Could you at some point not see through it?
Well, we don't know. Maybe we could do some experiment like that. My point here is that when I look through 3 feet of or 10 feet of water, I can see my reflection at the bottom of the pool. And we did the experiment here with Hans, where we put a mirror in a trash can at the bottom of the pool, and we filmed you only have air there, so you can see yourself. And you say, okay, no problem. There's nothing there, right? As if there is no air. Then we filled it with water, and we can see that the light continues to go through the water all the way to the mirror, comes back to our eyes. So light is going all the way. I mean, if we're going to talk about going through, light is going through the water and coming back up. Does the photon go through all those atoms back and forth?
Without hitting anything?
Yeah, without hitting anything. And when you have only air, it goes through all those atoms of air and comes back. When the light comes from the sun, it goes through all, I mean, we have air all around our planet, a very thick layer of air, because that's why we can breathe, right? And here we have the sun, this little photon. It's got to make it through all those gazillions of atoms all the way to your
And I
eye.
still think they're right. The more atoms that are between, the more atoms that are there, the more opaque the light gets. I mean, we know this because if you look off into the distance, which is basically you're getting the most air atoms possible. When you look off into the distance to a mountain, it gets like blurry because there's so much air between you and the mountain.
Is it? Or is it distance and dust and other issues?
Yeah, but I'm just saying, like, dust also counts. Like,
Yeah.
I think the more atoms you have, it does block light more, but not to the extent that you could probably block out light. Like, you'd have to have a lot of, because like even under the rope model, air molecules lose some of the torque or the torsion, the energy, whatever you want to call it, in the relay.
Yeah, and
So
that's
if
why
you have enough, it would lose all the frequency, or it would
possible.
retard the frequency down less.
Okay, but let's get to that point, because that's the other argument that these people make, and that's this one says, first of all, an atom is mostly empty space. So if an atom is mostly empty space, according to the official version, right, then all atoms should be transparent, all of them. We should see through cement walls. And so they say, okay, but the way they explain why something is opaque says electron absorbs a photon or energy, whatever you want to call it, and that's why it's opaque. Okay, great. What is transparency? Well, transparency, electron re-emits. It absorbs and re-emits. That's one argument they make. The other argument is the electron doesn't get pushed to a different energy level. Okay, so we have these two arguments. That if it doesn't, if the energy of the photon does not affect the electron that's rolling around, then it goes through and it's transparent. Otherwise, it's absorbed by the electron.
Why does it affect it in some cases and not in others?
Well, yeah, they haven't explained that. They
all
just say
have-
it is.
They all have electrons.
They say it is so. But there's a worse problem with that, and that's the more fundamental problem, which is the photon is a point particle and the electron is a point particle. And you're telling me that for all these photons that come in and all the electrons that are buzzing around in a material, air, water, whatever, glass, you're saying that all these photons that came through, they happen to hit that electron and knocked it into a different energy level? Is that what these people are saying? So yeah, there's a lot of
I
problems
think
with
we
that.
have the
explanation.
analogy for that. It's like a fly bumping into a mosquito in the Sahara Desert.
Yeah, more or less. And so
Oh, what are you doing here? Like, it's the only two in the desert, but they somehow find each other.
then we have reflection. They say, well, the energy bounces. In other words, the photon bounces. That's why you can see yourself in the mirror.
The photon bounces off the electron.
Or maybe it's against the proton. They never specify that. What is it bouncing against? But they just assume that you understand that the photon is hitting a brick wall and coming back when it hits the mirror. Okay, that's why you see
That I
yourself in
can
the mirror.
see because it's like a ball hitting the wall. And
Yeah, but when you
back.
get to the atomic level, now you're talking about,
Yeah.
did it hit an electron? Did it hit a proton? Did it hit a molecule? What did it hit?
Not only that, why does the mirror bounce it back better
Exactly.
than a wall?
Yeah, or when does it bounce it in a given direction?
Yeah.
Why do you see yourself straight in the mirror? When you stand straight in the mirror, you see yourself directly. All those photons are going back and going forward, and the molecule that makes up the mirror is not a very smooth molecule. So if it hits an electron, goes that way, and then it hits a proton, goes in a different direction. How many of them come directly at your face? And it turns out you look at yourself in the mirror, and it's
like
a mirror. It's a mirror
100%
image.
of them, yeah.
100% of them hit directly straight back to you. Okay, refraction, same thing. What happens there? They never explain it. They just introduce Snell's law, talking about angles. Okay, and they never say that's a description, mathematical description, not an explanation. So you never learn what it is. Diffraction, they say a photon can be at two places at once. Great. And then they finally.
That's all you got to say to that for that one? Great.
Yeah, I mean, who's going to believe it? I mean, what kind of explanation is that?
What do you have against the photon being in two places at once?
It's
not two photons, it's
no,
one in two
it
places.
does happen when I drink a lot of beer, then I see the photon at two places at once, but that's an observer related.
It falls apart.
And then at the end, they give you the icing on the cake. They say, we don't understand it, and that's philosophy anyways.
That's always the punchline, isn't
Yeah,
it?
so-
Why
so-
didn't I even come to you?
Yeah.
Where are the actual scientists?
Yeah, they say, study math and you'll understand it, okay? So we never understand anything from quantum mechanics, okay? So that's why, I have to explain the mechanism first, okay? Before we go into why this is opaque, why that is transparent, okay? And so here's one question, important question for the mechanics. Here you have particles representing the light, in other words, the photons, and then you have the waves, the famous transverse wave. And you have particles that travel slower and particles that travel faster. You have the same thing for the wave. So the question is, why can't particles travel faster than light? Why can't the wave travel faster than light?
Because then they'd bump into the guy in the front, right?
And yeah, so that's one of the questions that you really want to ponder. Okay, that's another issue that I raised this month. Okay, getting back to this, here we see the following. We have at least three proposals on the table. We have the particles, we have the waves, transverse waves, and now we have a new one since at least the beginning of this century, which is the rope. We're saying it's a torsion along a rope that physically interconnects any two atoms. Okay, so we have three proposals on the table. Okay. What's the problem with a wave? Well, here's the wave.
What is it?
Yeah, well, that's one issue. But here's the wave explanation. They say the wave goes through glass. Okay, and that's why they talk about traveling through. Okay, so they use that term, goes through, travels through. Okay, in the case of the rope, we're talking about relaying. Okay, there's nothing traveling, and so this is sometimes hard to get to people's brains because
throwing a ball is just easier.
Well, the one is that. The other one is that everybody's been drilled to exhaustion on traveling through. That's the only terms that they use. And I'm saying that under the rope model, you have to think in different terms altogether. You have to talk about relaying from atom to atom. There is nothing moving from left to right. The atoms are, I mean, for all we know, we could be moving to glass for sure. But if everything in the universe stayed where it's at right now, we would still have the rope torquing and the atoms pumping. So you don't have to have light moving from A to B. What you have is torsion. Okay, and so we have a different mechanism, and until people really get their brains around that,
it's a ball spinning a drill bit to pump a ball, basically.
Yeah, and what you're doing is relaying that signal to the other atom.
The ball pumps,
spins,
like torques the drill bit, and the guy on the other end gets the pump. He passes it on.
In fact, the torque goes both ways. Yeah, that's the other issue, weird. And that gives you an idea of what reflection looks like. Why reflection is straight ahead. Rope is taut. And when you look at yourself in the mirror, every atom in your body, every single one of them, is mirrored, to use that term, in the mirror. Okay, it's straight ahead, back and forth, along the same rope. Now it's easy to understand the mechanism. But when you say, well, hold it, the little particle hit the mirror, and why didn't it ricochet in, to the right or to the left? That's the question you got to ask yourself with particles. Waves, well, the question with waves is, we have no object called a wave. Okay, there's no object in physics called a wave. Wave is a verb. Okay, so you got to identify the object that is waving. The flag waves, but the wave doesn't wave.
Yeah, what are the arrows?
Yeah, and so the arrow right there, you see, vectors are represent quantities that have both magnitude and direction. So the arrows are vectors. What the mathematicians have done here is they put a mathematical concept and they represent it with an arrow. The arrow stands for a vector. What is a vector? It's magnitude and direction. And the worst part is they have these vectors moving. Very scary stuff.
Moving 3 north.
Yeah, you have a number that has direction, if you can conceptualize that. Yeah. You got to replace it with an Indian arrow, right? So you put an Indian arrow, you put a bunch of these Indian arrows that represent magnitude and then you put them in motion.
What's going on? It reminds me of the Dumbo part where Dumbo gets drunk and it's got all the pink elephants. He just starts hallucinating. It's like that. Like, what are you moving? What's going on? What is that?
So mathematics doesn't have a physical interpretation. So whenever you see a wave, ask, what is it that you're staring at? What you're staring at is a bunch of moving vectors. What is a vector? Well, it's something already in motion. It's a number in motion, number that has direction, right? And now they're going to move it in a different direction.
You can't move a number. Like, you can't move the number 3.
Well, it's worse when you try to move a moving number 3.
now
we got motion.
I don't know what you're talking.
We got 2 levels.
Did you understand? No. Well, go to the university, and then you'll not understand like we do at least.
Okay, and it doesn't stop there. We have the wave, which is nonsense. We have the particles, which are not particles. What you're talking about is a wave equation. You're talking about when you're talking about particle, you're talking about a wave function, whatever that means to you. It's just a number that they put at a location. They have all these locations moving. So they don't have a physical object. Ask any quantum mechanics, and if you say, well, do you really have a corpuscle there? And you'll find out what the answer is. The answer is no.
Is it a ball? Well, that's a metaphor. It's
they don't have corpuscles
representation.
anymore.
The number is a representation. It's a metaphor.
And so it's all concepts, especially dynamic concepts, which are also moving. And then planetary atom, nonsense. You can't explain why the electron doesn't fall to the center of the nucleus or why it doesn't drift away spontaneously. I mean, what keeps the electron faithful to the atom? That's what you got to explain. And if you cannot explain that, you cannot even start your presentation. Electricity, the flow of electron beads from atom to atom. What is what's coming in contact with each electron to move it? you got to explain this. You got to justify it. And they don't. They just say, well, electricity is the movement of electrons. Okay, what compelled the first electron to move? What came in contact with it? And what they're going to do is introduce a concept: force, energy, field. They can't tell you a physical object hit that electron, compelled it to move to the other atom, and supposedly it either hit the other electron and kicked it to the next atom, or that electron, for some reason, already left a hole, and this guy occupies it.
Whatever leaving a hole means.
Yeah. And so the question is, what triggered that first electron to move? I mean, what came in contact with the electron?
The light switch.
Yeah, but see, electricity is not really a light. It's not a photoelectric effect where you hit the electron with light. Okay, that's not what electricity is. Electricity works a little differently. Battery works chemically. And the question is, what triggered that first electron to move? Okay, we have the beginning of motion, which not even God can explain. Okay. What do we say? Well, light does not go through walls. Okay, it doesn't go through walls of bricks, walls of glass, walls of air or water. Okay. What we have is atoms attached to atoms, and the signal is relayed from atom to atom.
Are the brick wall atoms just greedy and they just don't relay it? Is that what it is? They just absorb the whole torque?
Well,
don't pump at all?
Right now, all I want to, before I get into that, because I don't want to get into that issue, right now, all I want to show is that first, quantum does not have an explanation for travel through. Because they have all these different interpretations, then they finally give up and we don't understand it, and it's philosophy anyway. That's in a nutshell.
Sometimes I wonder how much further down the rope hypothesis rabbit hole you would have gone if you didn't waste so much time with mainstream physics.
Well, you got to someone once told me, first you got to destroy quantum mechanics before you introduce your theory. Yeah. So part of it is criticism, and part of it is proposing an alternative. So I have both.
But again,
first I want to show what's wrong with quantum.
Yeah. But I just wonder how much that slowed you down. Like, because there's a lot of rope hypothesis mysteries that you can never really get to because you spend a lot of your time still just debunking what most people accept
take for granted.
Just on
well, that's true. I mean, I could look at different things that different phenomena out there that people have shown or seen in an experiment or observation or whatever. And so they say, well, how do you explain this? How do you explain that? And we could go into all that, but right now there's this big battle getting mathematical physics out of the way.
Well, a lot of it
all nonsense.
I think also it's more, if the rope hypothesis were at least accepted to the extent that people would run more experiments with it as a basis, then the experiments could have different conclusions.
Interpretations. Obviously.
Like
yeah. Okay, here we have the problem with speed. Good old Einstein is crying, as you can see, poor Einstein. Why? Because Einstein proved mathematically, and he's at least credited with having proved, that photons travel at a constant speed, and you do not add the speed of the train to the light that is coming out of the flashlight that you have on the train. Okay, so he said photon travels at the same speed no matter what. And it has a speed limit known as little c. Photons travel at 300,000 kilometers per second. But we could live with that because, otherwise we can't travel to the nearest star, even if we traveled at the speed of light, which we're a little distant from. And so the issue is that they had to invent this tachyon, and they also invented warp speed for Hollywood so that, the Enterprise could travel to Klingon land, at the speed of thought, you think, and you're there, okay?
Doesn't the tachyon come from the future or something?
Yeah.
He's running the marathon backwards.
Yeah, but again, they want to cheat. The point is they want to cheat on the speed of light. And why? Because imagine if NASA told you, look, it's confirmed, no one can travel faster than light.
I thought that was confirmed.
Yeah, I know it was, but they had to overrule that.
There's like an asterisk at the end of it, but
you have this loophole, to the law, and they had to do that because otherwise you'd lose hope that we'll never get out of this planet.
And if you lose hope, you lose backing.
And, NASA would not have funding.
Hurts the wallet when there's depression and
because why are we going to Mars? Assuming we ever get there, but let's assume that we send a few astronauts there someday. Okay, great. Does that mean we're going to colonize Mars?
Yeah.
And we say, well, yeah, we will. Okay, and the question is, what for?
So we have Earth 2.
Yeah, but Earth 2 is a quarter of the size of the Earth.
Yeah,
you got a little planet there, which you have to terraform.
Yeah,
right?
we terraform it like that.
Yeah, in a few 100,000 years.
You snap our fingers, it's there. It's badass. You don't want to go to Mars, man?
Yeah. In Hollywood, we can do anything.
Okay, one
but
thing.
that means you have your feet off the ground.
One reason for sure to go to Mars is kind of like my brother goes to Iceland with his wife, like to see the sights, the nature of it. When you on Mars, they got I think Mount Olympian or Mount Olympus or something.
Yeah,
It's
yeah.
like
The biggest
mountain.
one. Yeah.
Yeah, like just to see that, you're like, that's a tall. Imagine standing at the top of that, or be. I think they also have like a Marianas Trench kind of thing that's even deeper than the Marianas Trench. Just looking down that chasm would be cool.
Yeah.
But aside from that, it's just Earth again.
Okay, and yeah, here you have a proof that light not only travels faster than light travels instantaneously. It's known as entanglement. You know, they say one particle is connected to somehow. Connected with a.
It's connected to.
Yeah,
Like
you got to take that as a.
With a grain of salt.
Yeah, it's connected to another particle that's on the other side of the universe. When this particle goes clockwise, the other one goes counterclockwise. And if you turn this one counterclockwise, the other one instantly, gazillions of miles away, turns in the opposite direction. So they have all these explanations, these physical interpretations that involve not only faster than light, but instantaneous. In other words, you snap your finger, you think you're there, you're already there. So what have we learned about the physical, how Mother Nature runs her universe? That's the issue. You won't get it from mathematical physics or any so-called scientists out there, okay? What are the conclusions? Okay, here we have it. Light does not go through. That's the main point I want to make. It doesn't go through walls, through atoms, through molecules, through air, through water, whatever. It doesn't go through.
It goes to.
Right, it goes to, and then it's relayed, okay? So light is not made of particles or waves. Light is an interconnecting rope, okay? And again, it's relayed, and the speed of light is constant because of that. Why? Because you exchange frequency for wavelength, okay? And now with that, we can explain, you know, some things. For example, why reflection is instantaneous and straight ahead. I mean, every atom in your body is reflected not only instantly, you could say, right? I hate that word instantly because instant involves time, but it's straight ahead, first of all, and then it comes directly to you. And the only way you can really explain this is if you have a rope there and it turns in both directions, then it's easy to understand this. But if you say, well, hold it, the particle goes from my eye to the eye in the mirror and then comes back at the speed of light, is that what the particle does? And why does it bounce sideways or in a different direction?
The ball, it feels like it has room for error, like it could miss.
Yeah.
The rope can't miss.
Yeah, rope can't miss. Wherever you go, and here you see it, okay? This is the retroreflector stuff that mathematicians propose, specifically relativity. And what you have is the laser being pointed at the retroreflector on the moon, and that's it.
I like that gift.
Yeah, and we're not talking about flat earthers here who don't believe that we went to the moon or anything like that. But we put a retroreflector on the moon. In fact, there's 5 of them: 3 by the United States, 2 by the Russians. And what they do is they point a laser at the location, more or less, where the retroreflector is, and they get something back. And the question is, how do you show this with photons going one way? First of all, right? Because it moves, right? And so it's going through warp space on top of that, and both the moon and the Earth move. So how do you explain this? You can't explain it with particles. You can't explain it with waves.
You explained it right there perfectly. We caught the balls. We're playing ping pong with ourselves.
Okay, and and then the final one I want to show here is
like
under the rope model.
That's my
See how
favorite
easy
gift.
it is? If every atom on the Earth is connected to every atom on the moon, it doesn't matter if you put a retroreflector there, because every atom of the retroreflector is connected before you even start the experiment. Before you turn the laser on, it's already connected to that laser, okay, to whatever material makes up the laser. And so the moon can go anywhere it wants in the universe, and light will find it because light travels along the ropes that interconnect any two atoms.